start streaming. Welcome to functional programming. Studying functional programming. Yeah, so I stopped at the make triplets. I was in the last video I was reviewing the end of the second chapter. So, and also the kind of a really cool thing I want to try out. So I was using the GHCI somehow, and first I started with standard ML. So in standard ML, what is it? SML? Do I have it? SML, RLRep, SML. Right. So I've used this, and I wanted to use NICs. So now look at this. So in ML, you do like FN. Let's do val identity, FN of X. So that's like lambda X, and then this kind of a thing, which looks cool, but it's okay. FN X is like this. So we have identity, let's say 2. Oops, we have to do this unbound variable identity. Didn't I just bind it? Identity? Or I forgot. Unbound. What do you mean? Oh, I didn't bind it. Look at this. Val identity. I forgot. Okay, let's do it again. Val identity. Identity is what? Fn of lambda. So lambda x dot x, and then this thing, this semicolon. So now we have defined an identity in standard ML. Now if we do identity of 2, we get a 2. Now there's a lot of typing here, right? And then the next thing what I did was I tried the GSCI, so that's the Haskell interpreter, which is, cool. But in Haskell, it's a bit, different. At least we don't have to write val, but as a val, as in, value. And we don't have to write let. It used to be that you had to write let, but it's been not like that for like a couple of years. I think for like 8 years. I don't know. Okay, identity is, and Haskell has this way. So you write, you actually write the lambda like this with a backslash, x, and then this nice thing, x. So then you can use it, right? Identity 2. Oh, I've just changed actually my, anyway, okay. And then we get a 2 back, right? So that's the identity, how you define it in GACI. And I thought, I'm on Nix sauce. So I'm going to use Nix REPL, right? And Nix REPL, you could use it. I don't know how far you can use it because they say Nix is not Turing complete. Or it is. I'm not sure about that. Is Nix Turing complete? I'm not sure. I think it's a yes, it's complete. But who was saying that it's not? I read something about. Okay, so you can basically use, how did I name this stream actually? Studying Lambda Calculus to make a triplet. Okay, to make a triplet, right. Let's get back to this. Oh, it's really... Okay. Oh, no, I don't see the chat now anymore. All right. So, identity. So, we're going to use Nix REPL now. Okay, let's go out of the GHCI and let's go to Nix REPL. So in Nix REPL, it's kind of really, it's even more minimal, which is cool. So if you want to write, let's say the most simplest thing, it's the identity function. You write like this, x and a colon, and then just the x. And that's like the lambda. So the colon is like the dot. And everything left of the dot is like, it's the lambda head. It's the head. And everything right from the dot not from the dot, from the colon, right, is the body of the function definition, right? So on the left we have, so to say, the function name. No, that's not correct. It's not the function name, but the parameters of the functions, or how many parameters the function will take. And on the right side of the column, we have those arguments. Basically, we have the function body, where we write what we are going to do. So, so we can do like this, right? And if we just give it a 2, we're gonna get back a 2. So this is even a more minimal notation, and I kind of like it. And I mean, I just want to try in Nix REPL to continue doing this Lambda Calculus. So it'd be interesting. I don't know how far can I get. Probably far, because Nix actually is a purely functional lazy language, which is also nice, right? So you can define things, identity, like this also. Identity, and now we don't need the parentheses, x, and now we can use it, identity 2 and a 2, or you can use identity, I guess this would work also, identity 2. Yeah, this will work, identity on the identity. Now let's try to find other things. We did try to we found out, okay, I'm going to get back to this, make a triplet. But just want to try to define all the things that we've done so far, that I've done so far. So then we learned the self-apply, which is kind of a very nice way to be introduced to recursion. The self-apply is cool. So we have a lambda s. So we're not going to do any, so just like this, lambda x. So the self-apply basically just applies, it's like the identity function, but the only difference is that the self-apply applies that same argument to itself. So that's but this shouldn't work now. I don't think this will work also in Nix REPL. Look at this. Oh wow, how does this even work? This doesn't work. This is curious. Why does this thing work? This shouldn't work. This is kind of weird. This is very weird. Self-apply works because if you try to define this in GHCI, or I think also in other interpreters, it fails because you have to apply the arguments to itself. It's, how do you call it, circulatory. Let's apply, well, that's interesting. Let's try to see if, well, yeah, let's do the self-apply, and let's give it a 2. So if we give it a 2, it will apply 2 to 2, and then you see, attempt to call something which is not a function but an integer. Okay, let's do self-apply. And self-apply, well, we need a function, right? Let's do self-apply identity of 2. It's a 2. Well, yeah. Okay. Funny. Then we did the apply. Let's define the apply. So the apply is cool. So apply just applies something. It's kind of similar to self-apply, only because the things are not the same, right? So we have the lambda, let's call it, or like A, you can call it A, lambda A, and then when you have more lambdas in the body, you can do like this, lambda A, lambda B, and the apply takes A and takes B and applies A to B. So it's very, very simple. Takes A, takes B, and applies A to B. It's just very abstract, right? Like, because I think, and that's what I found out, and that's so nice about, Lambda Calculus is, it's almost like you are so used to working with some kind of values, even like in daily life. So when you just get these A's and B's, it's very so pure that it's almost like you can't, it's like it's very quiet. I don't know the word, because they describe some kind of relation, but nothing is being applied to it. So the relation is somehow, it's just very abstract in that sense. Not in abstract in the sense that it's too hard to understand, but it's very naive and I don't know the word. Okay, A and B. So, but now we are defining it in curried form. I wonder if this would... So look, you can now do apply identity. And then 2. It's the same as identity 2, but now you can use apply. Apply A, which will be identity, to B, which is 2. And we get a 2. I don't know if could you do, we don't have a defined plus yet though, but let's try just to see how it works in REPL. Apply plus to B. How are we going to define a B? Apply. Wait, let's just try something. Square. Although I'm cheating now a bit. It's just square would be A and A times A, right? That would be square. So let's do apply square to 2. Yeah, it works, you see. Even though square works too. Square 2, 4, and apply. And there is a whole, if you Google this, actually, I can't explain it. But what's the point of this apply then, right? You might say. There is a big point, but I can't explain it. And ChatGPT is also good about these things. I think I want to move the ChatGPT window because it's kind of, wait. Yeah. How do I move this? Can I move it? No, I cannot. Yeah, I've changed to... Maybe like this. No. No. Yeah. Complicated. Yeah. So now I've even lost oh, really complicated, yeah. And I lost the chat. Okay, I'll just stay here. I could use chat here actually. I like to use chat with voice. Okay, I'll just keep it like this. So, and then we did make pair, right? No, that we did the select first. Select first. So select first is a function, and there's so much beauty to this. So select first is also a combinator. Yeah. So the identity itself is a combinator at the same time, because it combines it does the most simple thing, the most simple combination you could do, right? Like if you give me a thing, you give me just one thing and I give you back that thing. That's the combination. You might say it's not what kind of a combination is that, but it's the most basic one. I guess it's the basic one, the identity of combination, right? It's to return the thing in some form, but this is the most basic form, is the identity. So in that sense, select first is a combinator. when you give me two things, I'm going to give you back the first thing. And that is also a combination, right? Combinators are, well, you can recognize combinators by, you know, all the variables are supposed to be bound in the head. So it's like if you give me two things and I give you back, I do something with those two things. We don't apply some third external thing to it. Then it's not a combinator. So it combines something from the input. And also they have bird names, which is kind of cute. So select first is kestrel bird. Okay, so select first is lambda A. Wait, lambda, no, I'm writing now like Haskell. So lambda A and lambda B, right? So we have two lambdas. And select first, we'll just take the first. That's our select first. And select second is lambda A, lambda B, and he takes the second thing. So now we have a select first. And also I mean, I said this is a combinator, but at the same time, this is actually a Boolean, because the first thing from two things is true. You can define it as true, and the second thing is false. So it's not speaking about the intrinsic, you know, value of truthfulness or something. It's just from two things. You have to decide, I guess. The first thing is true, the second thing is false, and then you applied some things, and yeah, then you get true or false. And in some sense, it is a conditional. I think it's so nice when you do the lambdas like this very slow and you practice substitutions and you apply them. It's really important to do substitutions, and then you almost start to think, you know, make up your own language, not your own language, but because there's so many A's and B's and A's and B's, so you almost like, I you know, wonder what would happen if I add more A's or more B's, you know. And yeah, it's interesting. So like select first, and we do hello Nix, right? Let's do hello Nix, and we get a first thing out of two. And select second, hello Nix, and we get a second thing next, right? Isn't that nice? And isn't that nice? And then we had a make pair thing, make pair, and that was kind of a mind-blowing moment, because the make pair doesn't actually make a pair. I thought it will make some kind of a pair, like a list. Not a list, but or like a tuple or a list or something, like some kind of a data structure, I guess, out of two things that I can call back. But when I don't call them, they're there. But it's not. Make pair somehow, it's a function that promises, you could say, that will apply a function to two things. But there are no two things. So like A, okay, the first thing, the second thing, and the function, and then F, A, B. So that's the make pair. But you still don't apply it. So you can do make pair. Look at this. And then I did make pair, hello, next. So that's the first naive idea, is that, but this won't work. Okay, it says it's a lambda string. I don't know if it will work with P. No, it doesn't work like that. I'm not sure how in Nix REPL you force evaluation. I think there is a way how do you force it. Yeah, like this. Ah, like this. Maybe like this. It just takes too long to do it like this. Yeah, I'll have to get back to my it works nice actually, but then when I have to change, yeah, next time I'll set up in different workspaces actually, not to have, Yeah, I shouldn't do this. It's with workspaces, it will be better. So I could, whenever I want to switch, whenever I want to, oh, this is nice, it kind of grows. Whenever I want to switch, I'll switch the workspace. Okay. So the make pair. So the make pair, and you see, wait a second, let's do colon P make pair. Let's try hello. No, it won't actually. You see, it just says there is a lambda, you know. So at first I was like, wait a second, but where is this pair? It doesn't exist. So you have to apply it because it's FAB. So you have to apply some function that will do something with the pair. So let's use our select first. So we do make pair, hello, and then next, and then select first. Isn't this weird? So now you do select first, and then what are you gonna get? You're gonna get a hello. And if you do select second, you're gonna get next. So it's very ephemeral. Like make pair promises that it will apply something to hello, to two, you know, arguments. And then you supply it, but then you supplied the function that will do what? You see, the make pair just says, I will apply this thing to two things, but you gotta give me the two things and what do you want me to apply? And then it does it, and we just get the result of the entire application, right? So it's not like make pair makes a pair. I thought like it will make a pair, like, you know, like hello, and then something like next. I don't know, you know, something like this. I will have a tuple. It will make a pair, like a concrete pair, but no. And then in the exercises, we did that. So that's kind of where we stopped. And then in the exercises, we had make triplet. So it says make triplet, define selector function. So define a function which is like make pair but constructs a triplet from a sequence of 3 arguments so that any one of the arguments may be selected by the subsequent application of a triplet to a selector function. Right. So define selector functions. So you have to make, well, that's not hard now, right? If we look at make pair, what's make pair? Right, it's lambda. I also wonder if I have to, because I'm writing this in actually curried form. So lambda A, lambda B, lambda F. I wonder if I could write just ABF and two colons. That would be actually in uncurried form. Let me try my make pair uncur. So that would be A, B, F, like this. Will that work? F, A, B. No, it doesn't. It does expect. Also, you know one thing that might pop in the mind? Why can I do this? Look at this. Make pair is, well, I'm going to apply a function to the first thing and the second thing. And it's going to look like this. Now, is this the same? Look at this, because if you notice, I did ABF, FAB. So I did the first. So I think this is not correct, because if you look at this, make pair is a function that takes the first argument and the second and outputs a function that takes a second and outputs a function that applies a function, some function, to the first and to the second. Now it's interesting because it's important really to set this in words. That's what I noticed, to know what comes first when you describe things. So it's not like make pair is a function that applies and you write f, because this thing won't work. Look at this, make pair. I just redefined it. So let's do hello, next, select first. It's not working. Look at this. It's showing Tim to call something which is not a function but a string. So it's calling a function and it's saying to me call something which is not a function but a string. So it wants to call a string. It needs the first, but the first is somehow now this f. So when we put a and b, then it will call the right thing. So you have to write make pair is a function that takes an argument a that outputs a function that takes an argument b and outputs a function that applies a function to the first and the second. So make pair is a higher order function. So it takes a function and applies a function. It's almost like a mapping. Like mapping, you map some kind of, let's say you map a square to a list of numbers and you list all the numbers in the square. So that's like make pair. Wait a second, could you do like make square? Yeah, I guess you could do this. Actually, this is kind of make square. Look at this, like make, okay, I'm just trying out. Make square is a, b, f. No, let's do make square a, f. So this is like our apply. And then f, and then a times a. Look at this, make square. So now it should do make square we don't have square. We have to have square as an f. Look at this, square. Square lambda f is, square is what? F times f. Or like x times, oh, f is, that's wrong. Actually, I defined it wrong. Make square. Make square would be this, lambda a. So it's a function that takes an argument and outputs a function that applies the square function, right, to an a. That's a make square. But now applies what? We have to define f as a square. No, I made things really complicated now. I just want to, basically I'm writing apply square. A, f. Well, square a. Or I could do make square a square. Look at this. I could do like this. N as in, you know, number. Could do even like this. Square number. And now what's a number? Well, I could give it some value, right? This is still untyped. So any number, and square should be some kind of a function. So square is a, so like n, and it will be n times n. That's a square. And now make square of 2. Let's see. No. Make square of 2 and square. Oh, now it works, right? Make square of 2 and square. So we apply square to 2. Yeah. So how do you make a triplet now? Well, just as you made a pair. It's just one more thing in the line. So let's do make triplet. Come on. Let's make triplet. As lambda A. So this is gonna be, I wonder if I can do, let's do like triple. MK, let's keep it short. MK triple. Lambda A, lambda B, it takes an A, right? Takes the first argument, takes the second argument, takes the third argument, and then takes a function that applies what? Well, applies something, right? A function that we're going to give it to what? To A, B, and C. That's a make triple. Now it says define selector functions. So triplet first. Okay, so cell first. Let's do cell first. Cell FST. Let's go like cell FST. Cell FST would be what? Select first from what? So select first from two functions was A, B, and A. That was the from two, but we have now three things, so we're just gonna add one more thing. A, B, and C, and we select first. So select second is A, B, and C. We're gonna select second. And select third. A, B, C, and C. And now we have it all defined. So look at this, make, now I even forgot how I named it, MK, you see, triple, is it like this? Make triple, okay. Wait, make MK triple and cell FST. MK triple is what? No, we have to provide three values, all right? Let's do, can we do characters like this? A, I think I can do the B and C. A, B, and C. And we're gonna select FST. So now this should work. It's gonna make a triple out of A, B, C, and select first is gonna select the first out of three things, which is going to be an A. No, invalid token. It does, oh, it can't take, okay. So let's maybe like this. Really, is it like this? So it selects the first, as you can see. It really quotes it. What if I do melee triple ABC cell FST? Yeah, it does an undefined variable. I wonder how do you take a char? MK triple. So let's try 1, 2, let's try 1, 2, 3. Okay, let's do like this. MK triple 1, 2, 1, 2, 3. Select second, it's 2, and MK triple 1, 2, 3. Select third, 3. Okay, so that's kind of clear. But the idea that comes, you know, I mean, after doing this for like a couple weeks, it's like, okay, I bet, you know, make pair. How do you create a real list? That would be probably mind-blowing. I think with MK, something has to do with these selects and the make pairs. I think something's going to be built on that, and we're going to create a list and the head and the rest. Like what's the select first is like the head of the list, right? And the what's the rest of the list? It's not the select second, right? What's the rest of the list? Or like the second thing is the select first of the rest of the list, but what's the rest of the list? You know, it's kind of, you start pondering. And how would you create a list with make pair? Well, this is kind of, it takes long, right? Look at this, make two, make a pair, make a triple, make a quad, you know, and you have to define all of these things. So probably defining a list and defining head and rest, it's going to be very relaxing kind of a thing, you know, and realization. It's really nice like this. I like to progress like this instead of just, hey, here's a list and here is how recursion works and that's it. Because you somehow, it's very important to build some appreciation. And then when you learn something, it you know, it becomes, you learn better. You learn better, you know. It sticks more. So define selector, which will select first, second, or third them from the triplet respectively. Show that make triplet item 1. Well, I think we show this. Item 1, item 2, item 3, triplet first. Okay, we did this. We just showed this. For the arbitrary arguments, item 1, item 2, item 3. Okay. Analyze each of the following lambda expressions to identify its free and bound variables. And those, maybe I can. And those in the sub-expressions. Oh. Lambda x and lambda y. It's funny, like you can even try. I wonder how it will be if I do it like here. Lambda x, lambda y. Will it work like this? Lambda x, x, y, and maybe not, lambda y, x. And maybe like, let's do it like this. Let's give it a y, let's give it a 1 and a 2. Well, no, it won't work. Hello, Nix. Unexpected. Expected. Oh, yeah. Okay. So let's try to do it then without... let's open up Helix notes. Okay. So what do we have? Oh, I didn't fix this thing. Oh. Keyboard. I have to change this. Did I change some stuff here? Configure switching. Because I enabled, there's this problem with remapping keys, caps lock, and it somehow doesn't work. Caps lock keeps on being backspace. Did I change it actually? Configure switching. Keyboard. Caps lock. No, it's just here actually. Where are the extra change? Preview enable. Key bindings. Configure keyboard options. Maybe this. Look at this. I didn't, but I have a service. Maybe Plasma can, because I didn't have that problem in Plasma. Let's try apply, switch, and then let's do. Ah, look at this. Oh. See. Okay. So what are we supposed to do? Analyze, identify free and bound variables and those in the sub-expressions. Well, lambda x, lambda x, lambda y, and lambda x dot y, lambda y dot x. So it's like, well, it doesn't look we have anything free. Lambda x is the head. That's the function head. This is the definition. But the definition itself has a lambda head, lambda y. And this is also, and it's being applied. So it's not, this is not a separated head. Otherwise it will be a dot, right? So this is the body itself, and the body itself, so this is almost like, when you look at it, it's like this lambda x dot, let's say you have y and some a. So lambda x and y, well, let's just lambda x dot x. You see this? So this is like this thing, lambda x, this is the head, and the x is being applied to x. Now, of course, this is the self-apply, but I just want to point out something else. So that we have, so this is the body itself, and there is, or you could say FA, right? There is some A here and a function here. This just looks wrong, but all I'm saying is to like to, you know, separate it in your head. This is the head, this is the head. This thing is being applied to this entire thing. But inside of this entire thing, we have two lambdas also. So we have a lambda x inside and lambda y inside. Yeah, I understand. It's kind of tricky. Like, is this y? It's a free variable compared to this one. And this x is a, because it's not bound in the head. But it's not free because it's bound with this one, with the outer head. And this y, yeah, this is tricky. I think this is about scopes. Oh. Wow, it won't just open it. Funny. Oh, it closed the thing. Wow, it did close the thing, really. Interesting. Why did it close the thing? ChatGPT. All right. So we have this thing, and I am supposed to find out the bound and unbound variables. Now it seems that there are several levels here in play. The outer lambda x and the inner lambda y. So the outer x, lambda x, is the function head. And then we have the function body, which itself has a lambda y that is being applied to an argument which is lambda x dot y and lambda y dot x. So inside of that argument, we seem to have free variables, because y is not bound in the lambda x, and x in the second argument is not bound in the head of lambda y. Now the question comes, if those free variables that only seem free from the inner scope are actually bound with the outer lambdas of lambda x and lambda y. That's a long one. This is a great question. And you're touching on one of the subtler aspects of variable binding, the distinction between bound and free in nested scopes. So lambda x, lambda y, lambda xy, lambda yx. Okay. Identify the structure. Outer lambda, lambda x. The variable x is bound within the entire body of this abstraction. So that's true. Yes, that's true. That's what's written in the book. So when you have a head, which is a lambda, right, we have the, like, this thing here. So this thing here, it's bound with everything that appears inside of its body is bound with the x here. So if the meaning of this is boo-boo, inside every variable named like this, it's going to be boo-boo. So lambda x dot lambda y, and then this thing takes a boo-boo. This here, actually, x. But what does the lambda x do? Why did I say boo-boo? Okay, the second lambda, lambda y, the variable y is bound within the body of this lambda, which includes the application lambda x dot y, lambda y dot x. So inside the application, lambda x dot y, x is bound here, and y is free relative to this lambda. Yeah, that's what we said. And lambda y, x, y is bound here, and x is free relative to this lambda. Free and bound variables in the nested lambdas. So let's take each subterm and determine the free and bound variables. Outer lambda, lambda x. X is bound for everything inside. We will analyze the body of lambda y, lambda x, y, lambda y, x. Second lambda, lambda y is bound for everything inside this body, yes, which is application of lambda x, y, lambda y, x. First argument, lambda x dot y. X is bound within this lambda abstraction. Y is free relative to this lambda abstraction, but is bound by the enclosing lambda y. Right. Second argument. Y is bound within this lambda abstraction. Final assessment. Okay, now let's return to your key question. Are the free variables in the inner scopes actually bound by the outer lambdas? Yes, they are. The y that appears free in lambda x dot y is actually bound by the lambda y in the second layer. Similarly, the x that appears free in lambda y dot x is actually bound by the outermost lambda x. So bound variables x bound by the outermost lambda x, y bound by the second lambda y, free variables. None. Right, that's what we thought. There are none. But it's from the, if you look at the things from the inside, they were free, but from the outside, they're not. So the inside lambdas don't know that. The outside lambdas do know that. Right. Because all variables in the term are eventually bound by some enclosing lambda. Key takeaway. Free variables are context dependent. That's good. A variable might appear free within a local lambda abstraction, but it could still be bound in the broader context of the term. Yeah, that's why you could have the same name. You could have the same name because the scope is different, but it could be named the same way. And I think later, because this actually, but this becomes just very complicated to, because you see the same term inside, outside, and it's difficult to follow. So I think later I think we will kind of use, you know, different terms, different names for this inside, outside thing. Right. Oh, I need to get back to. Well, on GNOME, this was actually much better, these things. No, I should do the. Yeah. How long was this? 3,000 kilobytes. Dropped frames. Okay, not bad. I think this might be actually better doing it in GNOME, in KDE than in GNOME. Interesting. Okay. Lambda x dot x, lambda y dot, lambda x dot xy x. And these things are good to solve on paper also. Yeah, but you cannot solve here much. Maybe if we apply something to this. Lambda x, let's do it. Lambda x dot x. Lambda x dot x. Lambda y dot lambda x dot xy x. Be interesting too. Oh yeah, this is going above. So what are free? Remove any name clashes in the expressions in exercise 5 above. Name clashes in the expressions. Probably it wants us to remove stuff like this. XA, right. That will be the second thing. So like lambda x dot lambda y dot lambda x dot y. This looks like kind of a little bit more boring part. So x and y, right? But I don't know name clashes. But there are no name clashes. Are there any name classes here? But are there any name classes here that we could rename? But that doesn't change the expression. Yes, there are potential name clashes in your lambda term, but these can be resolved through alpha conversion. The expression lambda x, lambda y, lambda xy, lambda yx identify the scopes. Now, the outermost lambda x binds x in the entire body. So I guess we cannot rename that, right? The next lambda y binds y. Yeah, inside lambda x dot y, lambda y dot x. This, I thought like maybe here A we could do, or like B and here A. Lambda x dot y, this is a new binding for x that shadows the outermost lambda x. So if we have a new lambda inside, it shadows. Right, that's called shadowing. So it's not reassigning, it's shadowing. The y here is free relative to this lambda, but bound by the outer lambda y. The y here is free relative to this lambda, but bound by the outer y. Well, this is a new binding for y that shadows the outer lambda y. The x here is free relative to this lambda, but bound by the outermost lambda x. So what, you just changed the name of these lambdas, I guess. We can rename bound variables while ensuring that the meaning of the expression does not change. The inner bound variables. Rename the x in lambda x dot y. Yes, x1 and lambda y1. Yeah, that's, so it's not this because this inside is bound with this, but free compared to this. It's interesting. Okay. What would be an example in Nick's language of such an expression? Let's say that the inner lambda x dot x, or the inner value of x is free but bound with the outer scope, and so with y. Maybe there is a simple example with packaging options or something like that, where we could have like two options bound with the outer lambda. Of course we wouldn't use lambdas, but the functional approach would be the same. Sometimes actually chat shows nice things when you ask something like this. Let's consider Nick's function for defining a package that has two nested scopes with potential name clashes due to reusing variable names. There is this rec thing also. Let outer options enable in what? Build enable. Let inner enable shadows the outer enable. Oh, in what? If inner enable, then package name enabled, else package name disabled. Yeah, it will be nice to show, lambdas. It would be nice to show some, context with these lambdas. That would be a nice approach I could try also, to find some examples in Nick's language and compare, it will bring more context. The options enable field is passed as an argument to the outer function and bound to outer option. Package name and option. Free variables. My package, let outer option, let. Is there a similar example in Home Manager module? Let's do this actually. where options are scoped hierarchically, and certain values can shadow or reference others in nested scopes. Yeah, we do this in Home Manager. And yes, look at this. Outer scope, global enable config programs neovim enable. Oh, he actually defined it. He put it in a name. I think this would be just like this, right? I've seen this in let. And then in what? Options, programs, neovim, enable, mk, right? Option, types bool, default false, description, enable neovim as the default editor. Yeah. But this is actually the module definition in Home Manager of the neovim. This is not like, because this is actually defining it, right? You wouldn't use this if you kind of just declare programs neovim. It will only be like what? It will be set default and then true or false. But here it's showing the entire definition. It's almost like if you wanted to write a neovim module, then you would write it like this: plugins, types, address of, types, default, global enable, referencing the outer global enable. Yeah, okay, that's enough of this. Not too much, ChatGPT. And yeah. So what do we have now? Lambda x dot x, lambda y dot, lambda x dot xyx. Whew. Lambda x dot, well, again we have a head. So we have a head here, lambda x, and this lambda x, so this x actually is bound with this x, right? And then we have a lambda y. Well, we could do as a practice. Okay, let's do this as a practice. Let's give it some values, right? Let's give it, well, we have the x and the y. Let's see what happens. Lambda x, let's try hello next. So lambda x dot x. So this is a. Well, let's do it with a and b. So look at this. A goes inside now. We cut the head, we remove the lambda x and we substitute a for the x inside. But the question is, do we substitute it also for this x and for this x? Let's try. So lambda x, we remove it. So that's a, and then lambda y dot, lambda x dot x is a, y, a, again we have the x, which will be a. Now let's substitute the b, a, lambda y, we remove the head, we have a and b, and then a. And now we are done. A, B, A. Actually, it's like this. A, B, A. And that's it. This is more, simplified. But that was not the question. What are free and what are bound? Well, do we at the end get the free ones? No. So this is the head, this is the body. And this is the x. Well, the x is bound, the y is bound. The y is the head. And then there's the lambda x dot x. Yeah, this is just interesting. ChatGPT. Outer lambda, lambda x. Right, lambda x. The variable x is bound in the entire body. Right. Body of the outer lambda. The body is an application of x to the argument. Right, that's also clear. So we have the head here, lambda x, and inside we have the application of the x to this argument. Identify free and bound variables. Innermost lambda x dot xy. Well, y is free in this scope. X is bound by the innermost lambda x. Y is free in this context, but will be bound by the outer lambda y. But it's just funny, like when this says that, does this means when we apply something to the outer y, we substitute this y as well? When you say, does this mean that when we, let's say, apply or input a value that is going to remove the outer lambda y, will that value itself go inside of this inner scoped lambda x that has a y that is from its own side free? Yes, when you apply, okay, when you apply a value to a lambda that has a free variable in its body, the free variable becomes bound if an outer lambda in the context binds it. Let's walk through your question with care. Yeah. Okay, that kind of makes sense. Okay, so we did this, and we have also here a b a b a b. So we have a lambda head here, a lambda a with the head, and this is the body. Inside of the body we have this is the same scope. Here now we have something different. So before we had this thing, look at this. Now we have lambda b dot a. This thing is going to be applied to this thing. So a is free, but bound outside with the a. Here we have lambda b dot the function name, and inside lambda a dot a being applied to b. So basically we have here an identity function applied to b, which is bound with this lambda b. But this b is not the same as this b. So I guess you could say b1 and b2. Yeah, because we have the same b's here. Interesting. Are the lambda b dot a, are these two inner lambdas? Let's say you have two inner lambda b's with their own bodies, and they are bound with an outer lambda b. So again, there is, wait, I could just copy it here. Browse, text selection. Yes, A is bound in the entire body, right? B is bound in the body of this lambda. Second inner lambda B is nested within the first, binds the body. This lambda A binds A in the body, right? And then free bound. A is bound in the entire body, right? First inner lambda B is bound within its body. A in this scope is free with respect to lambda B, but it is bound by the outermost lambda A. Second inner lambda B, B is bound in the body. A in this scope is free with respect to lambda B, but is bound by the outermost lambda A. Innermost lambda A is bound in the body, right? Analyze shadowing potential name clashes. We notice that the variables B and A are reused in different scopes. That's the thing, creating potential name clashes. So the first lambda B and the second lambda B bind different variables. So we could rename these guys. The outermost lambda A and the innermost lambda A bind different variables. Different variables. So rename the first B bound by lambda B to B1 and the second B bound by lambda B to B2. So lambda A, lambda B1, A, and B2. And lambda A1 and dot A1, B2. Right. Oh, I see. So we kind of see these layers. That's interesting, right? You kind of see them. So, okay, this could be shown. Okay, let's take this expression. Look at this. Right? So we have this. This can be shown like this. Lambda A, let's do it like this. Lambda A dot. Imagine instead of a dot, you do like this. And then lambda B, B1, okay. B1 dot, right? And now A, let's do the dots here also. So this is the dot. Lambda B1 dot. Is it dot? Lambda BA. Lambda A, lambda B dot A, and lambda B dot. Oh, this is like really tricky. So lambda B1 and A, and this lambda B2. Okay? Yeah. Lambda B2. Lambda BA. Lambda B1A. No, this is wrong. Lambda B1A. And lambda B2. Right, it should be like this. Almost like this. Lambda B2. Lambda B2 dot like this. Lambda B2. And now lambda A dot. Okay, lambda A. Okay, look at this. Lambda A dot AB. Right, now it makes sense. Okay, wait, if we, let's show it just like this. All right, look at this. All right, so these are the scopes. This is what you basically see in you're supposed to see this when you read this. One thing that's interesting is the dimensions. When we read text, we are used to reading from right to left, from left to right, or from right to left, but Basically, the point being we read in one direction. Here we read in one direction, but there is another like invisible kind of structure that you hold in your head. And this, I guess we kind of do that with code. When we write code, right, we don't write everything in a single line. And the way the lambda expressions are written is like this. And it's all in one big line. But actually, it's like this. And it's a little bit clearer like this, right? So there's the outer, and inside B1 and B2 are bound. Well, they're not bound. There's just B1 and B2. I guess you don't have to call it B1. Okay, it's calling it B1 because we have a B here. So I guess it would be, I think this is more consistent than just saying B and B1. Yeah, I guess that would be a very naive approach to have a B and then to have a B1. Or maybe B prime. Maybe B prime. Okay, but let's say we have a B1 that has an A and B2 that has another function with the head being applied A and B. Yeah. I'll make a print screen of this. Screenshot. What am I? Recording. I can record also. Interesting. Let's do like this. Save. All right. Not bad. Okay. So that's what, yeah. But you really have to do a lot of these, you know, and then you can see the code inside of your head, you know, better. But it's hard, yeah, at first. So we have a free, bound, bound, free, free, bound. So again, we have a free dot bound bound. Okay, so now again, but after a while, because it's kind of works in the same way, we have an outside head, right? So let's go level deeper. We have a bound. And then this thing being applied to this thing. So level deeper, level deeper. Now we are at the third level. Third level, bound, fourth level. Now it's a fourth level, right? Fourth level, and now on the fourth level we have this thing, fifth level, and then we have this thing, sixth level. Have 6 levels here. Free, bound, free, bound. Free, bound. Well, I guess you could say here free 1. Bound 1, bound 2, free 1, free 2, bound 3. Ah, that's like that. Okay. P, lambda Q. It just takes a lot of, it's very beneficial to do these things. I find it, and I'm just speaking from my experience. Because later when you see more complicated code, this somehow indirectly helps in understanding the scopes and everything much better, like really faster. Like you can almost see the scope as a picture, like a, you know, when I say like a picture, I mean you don't have to process the, you know, picture. I guess that's the goal, right? To see it like a painting. Well, let's say you see a painting of a sky and you just see the sky. It's not like you go, there is a cloud, there is a second cloud, oh, there's a bird. Oh, I mean, yes, you can do that, but it's not like you need time. Immediately you see, oh, a sky with a bird, right? And then you look at the details. But with code, when you're not so, you know, when you don't know what are you looking at, you start to like analyze, oh, is that a wing of a bird? Is it flying? Is this sky at all? Is this my home? Mm. Lambda P, lambda Q. But again, I'm just talking from my experience. I mean, I remember what, for some people, this could be, I think, yeah, this could be very easy, I guess. Lambda P, lambda Q. Okay, lambda Q. Let's go level down. So this is the body now. Let's go level down. Lambda R, another head, level down. So I have 3 levels here. And P what? Being applied to level down, level. It's a lot of level downs. Oh, but we have to apply the Q and P to it. But wait a second. Lambda R. Okay, so this thing here is being applied to Q and P. Maybe we could, substitute it and see what happens. Like this Q, this thing is going to go inside of Q. And then we're going to have a QP. Well, that's not the assignment. So level down. Okay. I'll just skip the 5th one. I'm really, remove any name clashes. But okay, we did something, I guess. It's good to do, I feel, progress. What's the time? Let's do a little bit more. I'm curious about conditions, booleans, and integers. So now we came finally to the 3rd chapter, conditions, booleans, and integers. We're going to define numbers. Hoorah! Introduction. In this chapter, we are going to start to add layers to the Lambda Calculus to develop a higher level functional notation. First of all, we will use the pair functions from chapter 1 to represent conditional expressions with truth values, true and false. So that's what, yeah. So select first and the select second, we're going to use them to represent conditional expressions, the booleans. Sometimes they say the boolean, with truth values true and false. We will then use these to develop Boolean operators like not, and or. Next, we will use the pair functions to represent natural numbers in terms of the value 0 and the successor function. Finally, we will introduce notations for simplifying function definitions and lambda expressions, and for an if, then, else form of conditional expression. So we will do branching, control flow. For the moment, we will be looking at untyped representations of truth values and functions. We will develop typed representations in chapter 5. I'm going to turn on the night mode. Can I turn on the night mode? Night light. Suspend. Configure, because my eyes hurt a bit. Day's light. Sunset, custom times. Can I just turn it on when I want? I don't know. Okay. Truth values and conditional expressions. Boolean logic is based on the truth values true and false, with logical operations not, and, or, and so on. We are going to represent true by select first and false by select second, and use a version of make pair to build logical operations. To motivate this, consider the C conditional expression. What do you mean, the C? The C conditional expression. Condition, expression, expression. Condition, question mark, expression, expression. If the condition is true, then the first expression is selected for evaluation. Right. And if the condition is false, then the second expression is selected for evaluation. For example, to set max to the greater of x and y. Oh, basically we have max now. To set max for the greater of x and y, max equals x greater than y, question mark, give x or give y. No. To set max to the greater of x and y, max x equals y, xy, lambda xy. Or what does he mean by this? Maybe he's just writing x or y. Or to set abs x to the absolute value of x. Abs x equals x less than 0 minus x lambda x dot x. We can model a conditional expression using a version of the make pair function. He's defining it. Wow. Let's do the cond. The cond, we have a cond now. Okay. Next REPL. Cond equals lambda E1. Lambda E1. Okay. Expression 1. No. Expression 1. So the lambda expression 1 and expression 2. Right. So the cond takes an expression 1 and then takes an expression 2 and then takes a function, right? Lambda c. C is the conditional, right? And does what? Look at this. Conditional expression 1 and expression 2 is almost like make pair. Expression 2. Consider cond applied to the arbitrary expression 1 and expression 2. Cond expression 1 evaluates to something, but then that itself is being applied to expression 2. Yeah, I'm still confused by this. So we need to do this on paper. I will need to do this on paper to get... Oh, now we're going to do this on paper. Right. So let's get back to our... right. Q. So notes, HX notes. So let's do lambda x, lambda E1. Or maybe let's do it like this. Maybe let's do it without the lambdas. We do it like in next REPL. E1, E2, C. Right. And now what do we have? We have CE1 and we have an E2. And now that itself is being applied to an expression x per 1, I will write, and x per 2. Expression 1, lambda expression 1, lambda expression 2, lambda c. That's the function head. So there are 3 curried functions. And inside, what are we going to do? We're going to apply C to E1 and then to E2. And we're going to supply them expression 1 and expression 2. It's just interesting that he wrote it like this. I think, well, we supply it inside. Okay, so now we do substitutions, right? So look at this. Expression 1, expression 2. Expression 1 will go inside of this head and we will remove E1. That's what I think it's going to happen without actually looking at it. So then we're going to have E2. Let's do just that. So substitute expression 1 for the E1, right? So then we're going to have E2, then we're going to have a C. We're going to just basically copy this, and not really. We have an E1 here in the body. So we need to substitute X per 1 here in the body, and then we have an E2, and then we're going to rewrite. We supplied the value, so we just write X per 2 now. What did he get? Did he get the same thing? E2, C being applied to expression 1, E2, expression 2. Right, that's the same thing. Now we're going to do the same thing with expression 2. We're going to supply to E2, we remove the E2 head. So we will just have a C then. C and C, expression 1. And E2 is going to be expression 2. And that's about it. So C, expression 1, expression 2. Now, if this function is applied to select first, we have a lambda C dot, and inside of the body we have, oh, I see, we have the cond. Oh, we do have the cond. What does it mean now? Now, if this function is applied to select first, what's going to happen if we apply it to select first? Let's practice that. C and then C expression 1, expression 1, expression 2, and then we're going to select first. So select first is going to substitute for the head, for the C. Right, this is not hard. So we're just going to have drop the C head and select first expression 1. And okay, this is actually going to look like this. Select first expression 1 and expression 2. What did he do? Right, selection first. Select first expression 1, expression 2. Right, it's the same thing. He only added the extra parenthesis here, but it's still the same thing. So now we have select first, expression 1, expression 2. And, well, select first takes the first, right? Will he actually expand on select? Well, we could do that actually, right? Let's do that because let's practice, right? So what's the select first? Now we need to substitute the function name for the function definition. So the function definition of select first is A, B, A. And expression 1, right? And expression 2. Oh, no, it's like this. So now look at this. Expression 1 goes. No. Expression 1 substitutes the A. And then we get a B. Because we dropped the A head. We get a B and A. Expression 1 is A. And then we still have the 2. So we have a lambda B, expression 1, expression 2. We substitute expression 2 for the B head. But this, so it chooses the first because it's almost like a cheating. It's not really cheating. It takes the B so that we can, remove it, I guess. It takes the B, but since there is no B in the body. So it takes the B, right? Right? You can do it like this. Right, I think there's a way how they do this. Expression 2, right? It takes the b, expression 1, and we remove the head, right? We remove the, you see this, we remove the head, but it takes the 2, but there is no b in the body. I think this is wrong how I wrote, but anyway, there is no b in the body, so it just drops it. And then we are just left with expression 1. And that's the final thing. That's the final countdown. No, it's not a countdown. Well, that's nice. I kind of like this, but it's I need to practice this a little bit on, paper. It really helps to have a piece of paper when you do lambda calculus. It's nice to write like this, but it just takes more time. With a pen and, paper works great. So that's the con. Now, if this function is applied, he does the same thing, we get 1. And if it is applied to second, select second. Now he does the second. The second is the same, only the end will be b. Expression 1, expression only here, a, b, b will be, we will have a b here. And expression 1 will go inside and it will be dropped because we will have a b. So we will not substitute the a for expression 1, which will leave us with lambda b dot b, expression 2, which will be the identity function. So we just drop it and we have expression 2, or you can say expression 2 substitutes for the head of lambda b, and inside we drop the head, and inside there is a b, and then we have the expression 2. That's the same thing. Notice that the condition is the last argument for cond, not the first. What? Notice that the condition is the last argument for cond, not the first. What's the condition? Did she write somewhere condition? Yeah, I don't know what he means by this. That the condition is the last argument for cond, not the first. Now we will use the conditional. Notice that the condition. What does he mean by that? Yeah, I don't know. I don't know what you mean. What do you mean? Really, how come I can't open? What does he mean by notice that the last and so on, the last sentence in this paragraph. The function cond is defined to behave as a conditional selector, similar to an if-else construct. Yeah, I think in Lisp is called, or scheme is called cond. It takes 3 arguments. So that's not the same as if then else or cond. Condition, a function that determines which branch to choose, select first or select second. Expression 1, expression 2, the value chosen if the condition selects the first, the value chosen if the condition selects the second. Cond, expression 1, expression 2, condition. Start with the full application of cond. Okay, now he does the same thing what we do. Notice that the condition is the last argument for cond, not the first. This emphasizes a key structural property of cond. The condition, select first or select second, is passed last, not first. Oh. Yes, the evaluation order proceeds by first partially applying cond to the values, constructing a function that waits for the condition to decide the result. I guess that's like make pair, right? We first applied this contrast with some other formulations, if in some programming languages where the condition might come first. In this functional formulation, the condition comes last to emphasize the compositional nature of functional application in Lambda Calculus. Does this have to do anything with like when we made make pair and we applied or supplied the select first after the make pair of two values? This has everything to do with how you made make pair, applied select first after constructing the pair. The con function described here or your make pair share the same underlying principle of higher order functions occurring. That's the make pair. A and B are two values being paired. F is a function that determines, so the select first or the select second that we supply that determines how the pair is used. Selectors. Select first picks the first value, select second the second. Applying make pair to select first. It's funny because you almost like think I will apply select first to make pair. And that's possible only if you add another lambda head so that you can substitute the make pair for the lambda head. I saw that in church pairs on Wikipedia. So you do make pair select first, and then the select first substitutes for the pair function. But if you wanted to really do select first make pair, you would have to write one more lambda head in select first so that make pair can actually come back to its place here before select first. Interesting. This gives you a function that waits for a selector f to decide how to process the pair. For example, applying select first, substituting select first, right? Expanding select first, and then you expand it, right? How cond is similar to make pair. Cond has this structure, lambda e, lambda e1, lambda e2, lambda c, c e1, e2. This structure is almost identical to make pair. Let's compare. It is almost identical. What did we have in make pair? We had A, B, F, and then F, A, B. What do you mean it's the same? It's interesting. Takes two values, A, B, returns a function waiting for a selector. Cond takes two values, E1, E2, it's just different name. Returns a function waiting for a condition, C. When you supply the condition select first or select second, cond resolves in the same way as make pair. Key difference, the order of arguments is what distinguishes cond from make pair. Why? The selector is applied after creating the pair. In cond, the condition, which is analogous to the selector, is the last argument, emphasizing how partial application can build functions step by step. But they are the same. They are the same functions. Cond could be easily defined in the same way by using A and B instead of x1 and x2 and F instead of C. Cond and make pair are structurally the same function. The only difference lies in the name of the parameter's semantic context. Look at it, it's the same thing. Yes, you can actually rewrite it. It's the same thing. They're functionally identical. But the distinction, it's so, isn't this amazing? Like you have a cond with make pair, just as you have a Boolean with select first. The distinction between make pair and cond lies purely in semantics. Make pair, the intention is to create a data structure pair and allow operations to extract. Yeah, well, you could say the cond intention to represent a conditional logic where the condition determines which branch to evaluate. But it's the same. This is a beautiful example of how functional programming and Lambda Calculus unify seemingly different concepts under the same mathematical abstraction. Fascinating. How long am I doing this? Hour and 46. Okay, I think that's enough for now. Where am I with the book? I think this needs to time. It's important to stop. You know, this needs time to like sink in a bit and do some stuff on paper. Maybe watch a video or something. Condition is the last argument for cond, not the first. To model some of the logical operators. Now he's going to do the not and everything. Okay, I'm going to stop here, and it was nice. Okay, so dropped frames. I'm not dropping frames. I was dropping frames when I was on GNOME. I don't know. Okay, bye-bye.